the new topic. Now, I remember when I started in this recap, we're talking about discrete random variable. The first member is actually Bernoulli. Okay, now Bernoulli is used to model, the random variable, with two possible outcomes, and of course, the numbers of trial has to be one. So the probability function for Bernoulli is actually this guy. Okay, and the state space is 0, 1. The numbers of trial here is 1. That is why the state space is 0, 1. Okay, and of course, the expected value of x is p, and the variance of x is p into 1 minus p. Now, when you take a look at this, x here represents the numbers of sources. I try once. This is like having one trial. Okay, I try once. It's either I see 0 success or 1 success, because the numbers of trial is 1, and that is why P here is the probability of success. X, the number of success. Okay, X, number of success. Okay, P, okay, probability, okay, of success. Okay, now if X is the number of success, okay, and I try once, then the numbers of failures is going to be 1 minus X. Numbers of failures is going to be 1 minus X. And what is the probability of failure? Is going to be 1 minus P. Okay, and 1 minus P, we can also call that Q, okay, which is the probability of failure. This is Bernoulli. Okay, we try once. Okay, it's either no success or 1 success. Now, from there, I'm going to go into binomial. So, okay, for binomial, okay, the probability of, the function is going to be n combination x, p raised to power x, 1 minus p raised to power that. Let's start from 0, 1, 2 until we get to n. Now, what is the difference between this guy and this guy? Okay, the two of them are talking about the same thing. Okay, the two distributions here actually model a random variable with two possible outcomes. Random variable with two possible outcomes, except that here, the numbers of trial is greater than 1. Okay, and that is why you see the state space starting from 0 and end up in n, depending on the numbers of trials. And if you take a look at this guy now, this is a probability mass function, okay, for binomial. Okay, now x still represents the numbers of success, p over there still represents the probability of success, and of course the only thing here is if x is the numbers of success, the numbers of failure is going to be n minus x. The numbers of failure here is 1 minus x. The numbers of failure here is n minus x. The numbers of failure here, the probability of failure here is 1 minus p. The probability of failure here is also 1 minus p. So what is going to be the expectation of x here? It's going to be np. What is going to be the variance of x here? It's going to be np into 1 minus p. That we can also write npq. Okay, where q equal to 1 minus p. Now, when you take a look at the two, okay, the moment you plug in, if n equal to 1, that will give you the mean of Bernoulli. If n equal to 1 here, that will give you the variance of Bernoulli. Okay, any question? Go ahead. Whether the formula will be given to you in the meantime, I think that should be the part of thing you should write in the cheat sheet. Does that make sense? We're not going to give you the formula. Because you know why? In the real world, when we encounter a problem, it's a formula to figure out? No, we're going to figure it out ourselves. So, okay, that's a good question. Now, the real-life application of this. I try once. How many success am I going to have? It's either 0 or 1. I try more than one time. How many success am I going to have? I could have 0, 1, 2, and so on. It's a possibility of the success. Okay? Now, I want to go into another review right now. This is Bernoulli. This is binomial. Now, another one is multinomial. If I don't want to consider two categories anymore, because right here, I'm talking about two categories. Okay, now if I were to talk about more than two categories, okay, I'm actually going to have the probability of this equal to that. Okay, I'm actually going to have this x1, x2, xk. Then I'm going to have P1 raised to power x1, P2 raised to power x2, pk raised to power sk. This is a multinomial distribution. How many P1 do I have? I got k numbers of P1, and that indicates k numbers of categories. Okay, k numbers of categories. Take a look at that. Now, when you take a look at this guy now, if I want to talk about expectation of x is going to be so many. It's going to be multivariate. Okay, so I'm only going to do this, MPI. Okay, which MPI means, do I want to talk about the expectation of x for category 1, for x1? It's going to be that. Okay, then the variance of that is actually going to be NP high 1 minus P high. Okay, where high is going to be one of the categories we are interested in. Okay, it's going to be one of the categories we are interested in. Okay, if you take a look at the three of them, right? If you take a look at the three of them, this guy here is a generalization of this guy in terms of the numbers of categories. This guy here is a generalization of this guy in terms of the numbers of trials. Okay? Now, this is that. Now, another distribution that I just want to review is Poisson distribution. Oh, sorry, let me go to hypergeometric first. Hypergeometric. Okay? Now, what is it relate? Hypergeometric and this guy, they handle the same thing. I'm going to say that again. Hypergeometric and binomial, okay, they got the same role. What is the difference between them? The difference between them is the mode of sampling. Here, sampling done without replacement. Sampling done without replacement. But while here, sampling done with replacement. Okay, now here, we're going to start with two categories. The probability of x equal to x is going to be, okay, I got k numbers of defective in general, okay, and the totality is n. So if I do n minus k, okay, that would be the number of not effective. Okay, if from a totality of what I produce, I want to choose a sample n, x is going to be the numbers of defective, and here in the sample, and this guy n minus s is going to be the number of non-defective. So if I classify this as defective and non-defective, okay, so here, x is going to start from 0, 1, 2, up to n, the state space, because the x here represents the numbers of defective in the sample. K here is the totality of defective in general. Totality of defective in general. This guy is the totality of non-defective in general. This guy is the totality of non-defective in the sample. Okay, so this is a probability. So the expectation of x here is going to be n k. Then the variance of x here is going to be n k this 1 minus this. Okay, this minus this. Okay, take a look at that. So if I were you, make sure you understand, what is it when you have a probability distribution, what is the expected value of x? What is the mean of x? Every probability distribution has both mean and variance formula. Okay, now the next that I'm going to review is Poisson distribution. And of course, I told you the other time, Poisson distribution actually model real event. Okay, actually model real event Poisson. Okay, Poisson distribution. The probability of x is going to be exponential raised to power lambda, lambda raised to power x over x factorial. And of course, x is going, the state space is going to be from 0, 1, 2 to infinity. It doesn't terminate. Okay, now, if I want to get anything here, I need to first figure out what is my lambda. You are likely going to be given lambda, or they give you something to calculate lambda. Of course, I told you lambda is going to be NP, right? Lambda equal to NP, okay? The expected value of x is lambda. The variance of x is also lambda, okay? Please watch out. Make sure you study that. So that's Poisson. So that is used to model real events. Now, another distribution in that family is a geometric, okay? Geometric distribution, okay? For geometric, you got P, 1 minus P, raised to power that, x start from 1, 2 to infinity, okay? Now, in the case of geometric distribution, how many failures or how many trials am I going to have before I record the first success? Okay, the other time I demonstrated, maybe I want to ask a question about a basketball game that I missed last night, and I decided to go from one person to the other, whether they watched the basketball game last night. And I said, you watch? She said, no, until I get to the first yes. Okay, that is geometric. I think I'm going to, for those of you in the United States, for those of you that follow politics in the United States, there was election. In fact, a particular election is going on in the House of Representatives now. They're trying to select a speaker. And to the best of my knowledge, the former speaker, McCarthy, I think was actually, they actually added like 15 ballots before it could emerge. Now the question now is, how many ballots are they likely going to have before the emergence of a speaker? If you want to figure out how you use geometric distribution. Okay, how many, from series of that before they now, get what they want. So that's going to be geometrical distribution. Okay, so the expected value, now S in geometric is different from X in binomial. X in binomial and Bernoulli represent the number of sources, but X here represent the numbers of trials, or you can say the numbers of failures. Does that make sense? Okay, now here, here is going to be 1 over P. The variance of X is Q over P squared. Okay, so this is the formula for geometric. Now, if I'm not talking about first sources now, okay, maybe has a question, no. I see yes now, another no, yes. This is a second yes, okay? Now, from the second yes, okay, then I'm going to have a generalization of geometric that we actually call negative binomial. Okay, the negative binomial is a generalization of this guy. We're not just seeing for success for the first time. Okay, we've seen success before. Okay, after success, we got some failures, then later see success. Okay, now the probability here is actually going to be this guy. Okay, now here, how here, okay, is the forces that we're talking about, not for the first time, because if R equal to 1 here, if R equal to 1, you are coming back here. You can put it, okay? Put R to be 1, okay? If R equal to 1, okay, you are actually going to go into that. Let's see whether that is actually, oh, sorry, it's going to be P raised to power R. Okay, so let's put R to be 1. That's going to be P, right? X minus 1, right? If R equal to 1, anything combination 0 is 1. Does that make sense? Mathematically speaking. So the expectation of X here is actually going to be R over P. The variance of X here is going to be Q, RQ over Q squared, RQ over P squared. Okay, so if you compare this with this, okay, when R equal to 1, it's going to come here. When R equal to 1, it's going to be this guy. Take a look at that. Okay, so that is the review of, probability distribution of the discrete. But before I go into, go ahead.
For the equation for like negative binomial.
When do I use what?
Like e to the r minus 1.
Oh, okay. There are two different versions of negative binomial. There is one that is p raised to power minus 1, but the one I'm using for this class is for p raised to power r. Does that make sense? Yeah, that's what I'm using for this class. Now, take a look at this question. In the exam, when they give you a question, nobody is going to tell you what distribution you're going to use. Okay, take a look at this. An oil company conducts a geological study that indicates that explanatory oil wells should have a 20% chance of striking oil. What is the probability that the first strike, that's a geometric. You'll be the one that will figure it out. That's a geometric because they say the first strike. The first strike occurred when? On the third. That means the first, no success. Second, no success. They record the first strike on the third attempt. That's a geometric question. So if you use this geometric formula here, you will get this result, 0.128. What is going to be your P? Your P is given 20%, is 0.2. Okay, you know your P. Okay, what is your X? Your X equal to 3 on the third. Does that make sense? That's super easy, right? Now take a look at this guy. What do you see? If you see anything other than first, or that's second, anything greater than 1, they're not just seeing success for the first time. That's a negative binomial question. Okay, the only difference between this guy and this guy is that your R will be what? R is going to be 2. Second strike. Okay, R is going to represent the number of success here. Okay, R is going to be 2. Okay, so take a look at that. Now, this is another negative binomial question in sports. I know some of you. So if we are told that the probability of Collie scoring a goal is 0.78, what is the likelihood she will make a 5th goal? Oh, 5th goal, which means this is not the first time he's going to be scoring goal. Yes, yeah, if she has been scoring goal, this should be negative binomial. Score, 5th goal on her 8th shot. Does that make sense? You are going to be the one that will identify, what kind of probability function you're actually going to use. Lastly, before I go into, there's another distribution called multi-hypergeometric. In binomial, we consider 2 categories, right? When the category is more than 2, we go to multinomial. Whether binomial or multinomial, we're sampling with replacement. Then what about if you want to sample without replacement? If it is 2 categories, we consider hypergeometric. But if it is more than two categories, it's going to be multi-hypergeometric. I want to take you to politics. Now, take a look at this question. Suppose there are R equal to 3 political party. Okay, I'm talking about United States now. Green, Democrats, Democratic, Republican. Now, the Senate consists of 100 senators. Of course, you know that. You know, when you want to talk about hypergeometric, we need a knowledge of the totality. This is not a sample size this time around. We're talking about an uppercase N, the totality. Okay, 100 senators, and K1 equal 45 Green Party, K2 equal to 20, and K3 equal to 35. Okay, now if you take a look at how many categories now they gave us the knowledge of what we are expecting in each category, and this category is more than 2. Okay, this category is more than 2. And when I choose here, I want to choose, I don't want to replace. I want to sample without replacement. Now, we want to choose a committee of N equal to 10 senator. Of course, in the House, you know, before a bill is going to go into the floor, you know, there's going to be committee, you know, that will look into that. You get what I mean? So, and at time they could have a bipartisan committee and stuff like that. They want to choose 10. If they want to choose 10, now the question now, okay, let Y1, Y2, Y3 be the number of each party members in the committee. Okay, now what is the probability we get 1 Green member, 6 Democrats, and 3 Republicans? Okay, now all we're going to do is how many Green we have in general 45. This is the totality for each group. Okay, if I want to choose, okay, maybe a green now, a green member will come from the totality of green member. If I want to choose Democrat, 6 Democrat is going to come from the totality of Democrat. If I want to choose 3 Republican, it's going to come from the totality of Republican. Now, this is it. They're divided by the sample space. This is a sample space because we actually want to choose 10 out of 100 senators. When you use a calculator now, you're actually going to figure out that probability. Okay, I want to go into today's topic. Like I said, I take my time to have a review on that. It is, for me, teaching is not, it's not about quantity but quality. It doesn't matter what the time it takes.